We are still on chapter 5. Last class, we talked about the Boyle's law, the Charles law, and the Avogadro's law. Today, we want to look at the ideal gas law. The ideal gas law. So by combining the gas laws, we can write a general equation. So we are going to combine all the laws, the Boyle's law, the Charles law, and the Avogadro's law. And when we do that, we have this equation. So R is a gas constant. So we can rearrange, we can rewrite it this way. PV equals to nRT. This is the ideal gas law. As I said, R is an ideal gas constant. So it's a constant. It has a value of 0.08206 atmosphere liter over moles per Kelvin. That is why your units must be in Kelvin. So let's try this example. How many moles of gas are in a basketball with total pressure 243 psi and a volume of 3.24 liters at 25 degrees Celsius? Take note of your units. We have to convert this psi to atmosphere and convert this temperature to Kelvin. So our volume, that's what we got. Our pressure, 24.3 psi. Our temperature is 25 degrees Celsius. We are searching for number of moles based on our question. So we are using the ideal gas equation. So as I said, make sure you convert them. Convert the pressure to atmosphere and the temperature to Kelvin. This is our gas constant. It must be given to you. So when that is done, we rearrange our equation. So this is conversion of psi to atmosphere. This is the conversion unit. Then converting degrees Celsius to Kelvin, this is the equation. So when you are done that, you are ready to go to solve. So you now substitute it in your equation. So this is our atmosphere pressure. Make sure you see this line here shows that our answer must be in three significant figures. So multiply it by the volume divided by the gas constant and temperature. And our answer is 0.219. Take note, it has just been brought to this. You will not get this in the calculator. Make sure you write your answer in the correct significant figure. Now I want to talk about standard conditions. Scientists agree on a set of conditions to report measurements so that comparison is easy. And we call this standard conditions. So often referred as STP. STP simply means standard temperature and pressure. That's all. So when you see STP, you should be able to know the value. What is the standard temperature? What is the standard pressure? So the standard pressure is 1 atmosphere. That's it. And the standard temperature is 273 Kelvin, not 25 degrees Celsius, I said. This is equal to 0 degrees Celsius. So it's 273 Kelvin, not 25 degrees Celsius. So same gas, different conditions. Consider ideal gas that occupies a volume V1 and has a temperature T1 and pressure P1. So our equation will be this or this. If the conditions of the gas are changed to P2, V2 and T2, then our P2 times V2 will be equals to nRT2, or N will be equals to P2 times V2 over RT2. If you notice, N is not changing. N is still the same. The number of particles is still the same. So we can combine the two equations because the N is the same as P1 times V1 equals to T1. Sorry, P1 times V1 divided by T1 equals to P2 times V2 all over T2. So let's use that to solve our problem. So a gas occupies 10 liters at 3 atmosphere and 300 Kelvin. What volume will it occupy under standard condition? So we are searching for the volume it will occupy under standard condition. So let's look at V1. 10.0 liters. Let's P1 equals to 3.00 atmosphere. Let's take a T1. T1 equals to 300 Kelvin. So standard temperature will be as T2, which is 273 Kelvin. And standard pressure is 1 atmosphere. So we know that P1 times V1 all over T1 equals to P2 times V2 all over T2. So P1 times V1 all over T1 times T2 all over P2 equals to V2. Take this T, go up here, take this P. So now let's substitute. So V2 equals to, what's our P1? P1 is 3.00 atmosphere. Times what's our V1? V1 is 10.0 liters. What's our T2? Our T2 is 273 Kelvin. Our T1 is 300 Kelvin. and our P2 is 1 atmosphere. So cancel the unit, take care of the units. We are left with volume. So volume is correct. So now 3 times 10 times 273 divided by 300. So what we have is 27.3 liters. So that's our V2. So now let's look at molar volumes. Solving the ideal gas equation for the volume of 1 mole of gas at standard temperature and pressure gives 22.4 liters. So 6.022 times 10 to the 23 molecules of gas will occupy a volume of 22.4 liters at standard temperature and pressure. So as I was saying, solving the ideal gas equation for the volume of 1 mole of a gas at standard temperature and pressure gives 22.4 liters. And 6.022 times 10 to the 23 molecules of gas will occupy a volume of 22.4 liters at standard temperature and pressure. We call the volume of 1 mole of a gas at standard temperature and pressure molar volume. We call it the molar volume. It is important to recognize that 1 mole of different gases have different masses, even though all of them have the same volume, 22.4 liters at standard temperature and pressure. All of them have the same volume, but their masses are different. So we can see this. So this is helium, 1 mole of helium, 22.4 liters. 1 mole of xenon at STP, 22.4 liters. 1 mole of methane at STP, 22.4 liters. So they are different gases, different masses, but at standard temperature and pressure, all of them have equal volumes. So let's try and do this example. How many liters of oxygen can be made from the decomposition of 100 grams of lead-4 oxide at standard temperature and pressure? So this is the equation. This is the equation that represents the decomposition of lead-4 oxide. This is the equation. So how do we process this? We have to convert this to number of moles of lead oxide, the mass of lead-4 oxide. We find the moles, and when we get the moles, we convert it to number of moles of oxygen. Then, from number of moles, we can now find the volume of oxygen produced. So 100 grams of lead-4 oxide, this is the balance equation. We need the volume of oxygen. So this is the plan. Move from mass of lead-4 oxide to moles of lead-4 oxide to moles of oxygen to liters of oxygen. So look at the conversion factors that we are going to use. This is the molar mass. And this is the mole ratio of oxygen and lead-4 oxide from the balance equation. So those are the conversion factors. Now we set them up. 100 grams of lead-4 oxide. The mole ratio to convert to number of moles. This is the molar mass of lead-4 oxide. You get the number of moles. Then mole ratio. This is mole ratio from the balance equation. We convert to number of moles of oxygen. Then we take the molar volume, which is 22.4 liters of oxygen, and we get. So the volume that we are going to get of oxygen from this reaction is 4.68 liters of oxygen. When we talk about standard density conditions, density is the ratio of the mass to the volume. So density of a gas is generally given in grams per liter because gases occupy a lot of volume. So mass of 1 mole of gas equals to what we call the molar mass. So volume of 1 mole of gas at standard temperature and pressure is 22.4 liters. So our density is molar mass of the gas over the molar volume of the gas, which is 22.4 liters. Molar volume of the gas. So we want to calculate the density of nitrogen at standard temperature and pressure. This is the molar mass of 1 oxygen atom by oxygen molecule multiplied by 2. So this will give 28.02 grams per mole. So we want the density. So we are going to use the molar volume and the molar mass of oxygen. So this is our equation. I mean of nitrogen, sorry. So you do the same for oxygen too. So when you do that, the density of nitrogen is 1.25 grams per liter. So this is the molar mass over the molar volume, and that will give us the density. So gas density. So gas density. So we know that mass equals to moles over times moles over molar mass. Give us the number of moles. Because mass will cancel. Therefore, moles equals to mass over molar mass. So density is mass in grams over volume in liters. So this is the ideal gas equation. We are going to substitute for N. So this moles is N. So we're going to substitute for N here. And when we substitute for N here, we have P times V equals to mass over molar mass times gas constant and temperature. Then we are going to take, we want to rearrange this. P times V equals to mass over molar mass times R times T. So we are going to take this P, we multiply it by the molar mass. So we are going to, let's do it again. I just need some space so that I can do this. So P times V times molar mass equals to mass times R times T. So I want us to bring volume this way and take RT this way. So our P times V, volume has to go the other way. P times molar mass all over R times T equals to mass over volume. And we know that mass over volume is density. So density equals to pressure times the molar mass over R times T. So that's what I'm trying to show you people. So this N is substituted here. This is N. Then you rearrange it. Take the V, bring it this way. Take RT, bring this way. You get this, which is density. So density equals to pressure times molar mass over gas constant times temperature. So let's find the density of nitrogen. So calculate the density of nitrogen at 125 degrees Celsius and 755 millimeters mercury. So what do? We need to get these units, change this unit to degrees, to Kelvin, and this to atmosphere. Then we can find the density. So that's what we got. So this is the unit to change to atmosphere, and this is the unit to change to Kelvin. This is our molar mass of nitrogen. So we get the atmosphere, we get the temperature in Kelvin, then we substitute it. So we substitute it in our equation, and the density of nitrogen comes up to be 0.852 grams per liter. Let's take another example. Calculate the molar mass of a gas with a mass of 0.311 grams that has a volume of 0.225 liters at 55 degrees Celsius and 88.6 millimeters mercury. We want the molar mass of the gas. So we have the mass, we have the volume, we have the pressure, and we have the temperature. But take note, we have to convert the temperature to Kelvin, and we have to convert the pressure to atmosphere before we can substitute and get our molar mass. So we do this conversion. On this. This is our equation. But we know that then this is our molar mass, m over n. Let's not forget. But we have to find n first using this equation. PV times nRT. We are going to use this to find n. Then we use this to find the molar mass. That's for n. Then that's for the molar mass. So convert to atmosphere first. Kelvin. Then now we want to find n. We use this equation. So our n is 9.7454 times 10 to the minus 3. 3 significant figure, 10 to the minus 3 moles. Now we rearrange this to get our molar mass. So our molar mass is m over n. And the molar mass of our gas is 31.9 grams per mole. So that is how we find the molar mass of a gas. We want to talk a little bit about the partial pressure of gases. The pressure of a single gas in a mixture of gases is called the partial pressure. We can calculate the partial pressure of a gas if we know what fraction of the mixture it composes and if we know the total pressure. So we must know the fraction of the gas in the mixture and we must know the total pressure. If we know the number of moles of the gas in a container of known volume and temperature, we can be able to calculate the partial pressure of the gas. So Dalton's law of partial pressure, what does it state? It states that the sum of the partial pressures of all the gases in the mixture equals to the total pressure. So the sum of the partial pressures of all the gases in the mixture equals to the partial pressure. Equals to the total pressure. Equals to the total pressure. So, for example, the composition of dry air. This is the composition of dry air. We have 78% as nitrogen, 21% as oxygen, 0.9% as argon, then 0.04% as carbon dioxide. So partial pressure of gases in a mixture can be calculated using the ideal gas law. We can use the ideal gas law to calculate the partial pressure of gases. So for two gases, A and B mixed together, the partial pressure of gas A is Na times R times T over V. The volume is the same. The two gases they are in the same container. And P is NB times R times T all over V. So the only thing that is different is the number of moles of the different gases in the mixture. So the temperature and volume of everything in the mixture are the same. So N total equals to Na plus Nb, which results to P total to be Pa plus Pb. And this is equal to N total times R times T all over V. So we want to find the partial pressure of neon in a mixture with total pressure. Remember, we have total pressure of 3.9 atmosphere. Volume is 8.7 liters. Temperature is 5.98 K. And the mole fraction of xenon is 0.17. So, in order to solve this, we have to find the partial pressure of xenon because we already have its number of moles. Then we subtract it from the total pressure to get the partial pressure of neon. So that's what we have to do. Get the partial pressure of xenon. We subtract it from the total pressure to get the partial pressure of neon. So that's the total pressure, that's the volume, that's the temperature, that's the number of moles of xenon. We want the partial pressure of neon. So we have to find the partial pressure of xenon first, then we subtract it from the total pressure. So that's what we are going to do. So that's our ideal gas equation. We'll use it to find the partial pressure because N is different. Then we subtract it. So that's what we are going to do. Let's see what we are going to do. So partial pressure of xenon, that's the number of moles of xenon gas constant at temperature over volume. And this is our partial pressure of xenon. We are going to subtract it from the total pressure. So 3.9 atmosphere minus 0.9589 atmosphere. So this is the partial pressure of neon. We want to look at mole fraction. The mole fraction is the ratio of the moles of a single component to the total number of moles in the mixture. That's mole fraction. And the equation is Na over N total. We normally use this symbol to represent mole fraction. So Pa over P total equals to Na over N total. So Pa equals to mole fraction of A times the total pressure of the gases. So find the mole fraction and the partial pressure in a 12.5 liter tank with 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. So let's try and solve this problem. So we have the mass of helium that's given. We have the mass of oxygen, 4.3, 2 grams. We have the volume, the total volume of the tank, and the temperature. So we are going to find the mole fraction of helium, mole fraction of oxygen, then the partial pressure of helium and the partial pressure of oxygen. Then we are going to find the total pressure. So from the mass, we are going to get the number of moles of the different gases. Then we'll find the mole fractions. From the mole fractions, we are going to get the partial pressure of the different gases. Then we are going to sum them up to get the total pressure. So from the partial pressures, we are going to get the total pressure. So let's start. We have our units here that we are supposed to use. That's the gas law. That's the gas constant. This is our equation to find the partial pressure. These are the molar masses of these gases. So we find the number of moles of helium, 6.05 moles of helium. We find the number of moles of oxygen, 0.135 moles of oxygen. Then we find the mole fraction of helium. That's the mole fraction of helium. You see, this is the number of moles of helium all over the total number of moles of both helium and oxygen. You sum them up. So this is how you get the mole fraction. So the mole fraction of oxygen is the number of moles of oxygen all over the total number of moles. That's it. Then now I want to find the partial pressure of the gases. So this is the partial pressure. This is the total pressure. So you can just sum up the total number of moles of the gases and get the total pressure directly, or you can find the partial pressure of the gases and sum them up. It will still give you the same answer. So, but to summarize everything, sum up the number of moles of the gases, put it in your ideal gas equation, and you get the total pressure of the gas. So this is the partial pressure for helium, and this is the partial pressure for oxygen. You see the partial pressure of oxygen. You sum these two, you will get this value, 12.099 atmosphere. Or you can do it this way. Any of them will give you the same answer. Here they use the total number of moles and solve and got this, but you add this and this, you get the same answer. So that's what I'm talking about. So there are two ways you can do it. You can do it this way, or you can do it this way. So we are going to stop here for now. We'll continue with collecting gases. Thank you for coming to class.